7, which is 111. This is the one that gives you minus 8.
I understand, but the thing is, how is this, handle?
Okay, I'm gonna give you a brief write-up. I'll post it and look at it.
I'll just write through the textbook I have for my season.
All right. And I'll post it for you.
Okay, sir. All right, everyone. Let's get started. So, yeah. A lot of hard work. So I'm going to show you guys today how to do the 4 8x8-bit multiplication way that Professor Eldon was sort of getting to, where he drew a square with 4 boxes. But I'm going to do it with a much simpler example. So I'm just going to do 2 8-bit signed numbers multiplied together. So what it's going to break down into is 4 4-bit by 4-bit signed binary multiplication. So I just came up with some examples. So let's say for A we have minus 112, and as a signed representation that gives us OX90, B is 35, gives us OX23, and then the result that we want at the end is minus 3920, and that's what it's going to be. So what you can do, I call it the naive way, is where you're going to just do multiplication on the magnitudes of A and B, and then figure out the sign at the end. So if either A or B was negative, you're going to get a negative number. But if both were negative, then you can just leave your result because you want a positive value. So the first thing you would want to do is find the magnitude of minus 112. So you would do your 2's complement operation, just flip all the bits, add 1, and you get OX70. And then just for the sake of breaking this problem down into simpler steps, I'm calling the lower 4 bits in the A low and the higher 4 bits A high, and then the same for B. So that's what we get. And then I'm going to break this down into 4 steps where I find the 4 8-bit products of A low times B low, A high times B low, A low times B high, A high times B high. So this gives us 4 8-bit values, but we're looking for 16 bits. So how are you going to use these 4 8-bit things to come up with 16 bits at the end? So the first step we're going to do is just do AB low low, which is just AB low times, or A low times B low. So just going through this, it's just like regular binary multiplication. So you're going to get 0, 0, 0. I mean, you can see that since this is all zeros, we're going to get zeros at the end. So I'm just going to write all zeros, or 8 bits. 1, 2, 3, 4, 8. So that's the result that we're going to get. I mean, we could just work it out like this. It's going to be the same. And you see that from this, we just got 7 bits. So when you do it this way, since we changed the magnitude back to, or when we got the magnitude of these numbers, we're just going to get a 7th bit. But we might have some carryouts depending on what the values are. So that's what AB low low is. And then we want to do AB high low. So what this is essentially doing, it's just like doing regular multiplication. Let's say we have 32 times 25. So what that does, what this algorithm is essentially like emulating, it's doing 5 times 2 equals 10. It's doing 5 times 30 equals 150. It's doing 20 times 2 equals 40, and it's doing 20 times 30 equals 600. And then when you add those all up, you get the correct product that you're looking for. So this algorithm, basic one, using splitting it up like that, think of these 4 operations that we're doing here as like a breakdown of these sort of 4 operations where we looked at the different place values. So we did the first one, which was just 0, 0, 0, 0, 0, 1, 1. Sorry, one sec. There you go. And then now we want to do AB high times B low. So from here, we know that the high bits was 7, or hex value of 7. That gives us 0, 1, 1, 1. And then when we multiply this out, we're going to do the same thing. So since this first least significant bit of B low is 1, that means I'm just going to write A high over here. So 1, 1, 1, 0. We're going to do your shift. Since it's a 1 over here in this position, we're going to do just write A high. So then we're going to add those. But you see that we shifted it left. So you can do the same thing. And then since these two are zeros, we can just write zeros over here. Then now you want to add them up. But so going through this algorithm, it's a little deceptive the way I'm adding it, because what you're going to be doing in your algorithm in the actual assembly code, you're not going to be adding all these up at once. You're going to be adding them up within a loop. So I hope you guys understand that distinction. So this is just showing it from like a high-level point of view, almost like stepping through it. So when you add those up, 1, and then you get a 0 here, and then you have a carry of a 1. So that's going to give you 1 here, and then another carry of a 1. So 1 plus 1 is 0, and then there's a carry coming from here, and then 1, 0, 0, 0. Double check that. Yep. So now you want to do AB low high, so it's A low times B high. So if we go look at this, we have in the least significant bits, we have a hex digit of 0 for the magnitude of A, and then for B high, we had 0, 0, 1, 0. So since these are all zeros, it's going to be zeros. Add all those up. Now we have the last part remaining, which is A high times B high. So A high was 0, 1, 1, 1, because that's a hex digit of 7. And then B high was 0, 0, 1, 0. So let's write that in. And then just going to do binary multiplication the same way. So since this is 0, we're just going to write zeros. And then now we look at the next bit right here. So since it's a 1, we're just going to write A high. Since these two are zeros, we're just going to write zeros for the rest of them. Then you want to just add them up. So that gives us our 4 8-bit values that we have, and we need to figure out a way to make those into 16 bits and get our magnitude of that product. And then we're going to look at what the sign bits were of the original operands, or A and B, and see if we need to do a 2's comp or not, or just leave it alone. So I'm just going to copy this part. So the way I've shown this part, too small. Let me just zoom out a little. So this is 16 bits, just to show you of what things might look like in memory. So for problem 17, you're going to have a 32-bit result spread over 4 bytes in memory. So what this picture means is it's just going to help you show what products you need to add together and at what positions, and then how you're going to do carries if you have any, and then do 2's complement after that. So we had that for AB low-low. For AB high-low, we had this. For AB low-high, we have this, and then AB high-high, we have that. So remember at the beginning of this example, I said that we're emulating, let's say our registers were like 4 bits. Because I'm doing a smaller example of what problem 17 is. So instead of doing 16 bits, I'm 16 bits. I'm doing 8 bits times 8 bits, and then emulating if your registers were 4 bits. So when you set it up like this, you as a programmer know what you're going to be adding to get the correct values. Oops, this isn't correct. So these like places where I'm writing an X you're not going to be adding anything to it. So this would be your first addition that you would have to do at the end to get the least significant bits. Yeah?
How do you get those offsets?
So I'm just pretending you as a programmer know what these offsets would be. So since we only have, I don't know why this is blue, but since we only have, we're thinking of things as a 4-bit register instead of an 8-bit register. So this value would be stored in one register, for example, and then this value would be stored in another register. So doing this exercise shows you what registers you need to add to get the least significant bits, and then like piece it together at the end. Let me make this not blue. So what you're essentially doing is, from AB low-low, if you look at the 4 least significant bits, those are going to be your 4 least significant bits of your product of the magnitude of it. So you don't have to add anything to it. You would just directly write those values down here. And then to get the next set of 4 bits of the more significant bits, you're going to be adding the high part of AB low-low. So remember that these were all 8 bits, 8 bits, 8 bits, 8 bits. So we're just going to be adding the high part to the low parts of these two. And then we don't care about this one. I think my alignment might be off. So when you add it up together over here, you're going to get 1, 0, 1, 0, and then we're just going to be doing the same thing. So all that white space that you see, we're just filling it with blanks. We don't care about what they are for those positions, because AB low-low has no effect on the high order bits or the more significant bits of your product's magnitude. You get 1 here, 1, 1, 1, 0, 0, 0, 0. So this gives us our magnitude of A times B. So what we need to do from here is go back and look at what A and B were, and we know that A was negative. So negative times a positive is going to give us a negative. So that means that this magnitude that we got, we need to take the 2's complement of it. So how do we do that? We're going to do just 1's complement and add 1. So we're going to flip all the bits. And add that 1 right over there. So when we do that, we're going to get 0. We're going to have a carry of 1. We're going to have another 0, carry of 1, another 0, carry of 1, another 0, carry of 1, 1 here, zero, 1, 0, 0, 0, 0, 1, 1, 1, 1. So, I already had it here. Delete this row. So this would be our result, and what that is OX, if we look at this, F, 0, 1 plus, or 8 plus 3 is 11, so B, and then 0. So is that what we were looking for? Yeah, F0, B0. So that gave us the correct value of signed 8 bits times 8 bits. But I broke it up into 4-bit by 4-bit. So for your programs, you're going to be breaking up your 16 bits times 16 bits signed into 4 8-bit by 8-bit if you go with this method. This is just one method. I'm sure if you guys have been to office hours, the other TAs have been showing you guys other methods where you don't do it this way. You can use 2's complement to do that. And I made another small example to show the other way. Yeah?
So the numbers are both given to you in 2's complement.
Yeah, so the numbers A and B, they're given to you as signed values which are in 2's complement. So what this problem did was it took your negative values and just converted them into positive values. And then you just did regular multiplication, which is unsigned binary multiplication. And then at the end, you took 2's complement, depending if one of the multipliers was negative. Yeah? Okay. So think of this example. So when you do 5 times 2, you're doing the ones place, you know? So it's the similar thing that you're doing when we stack them here. So when you get 5 times 2, you get 10. When you do 5 times 3 here, you're not doing 5 times 3. You're really doing 5 times 30. So that may be a little confusing. Let me show you what it is over here. So when we do A high times B low, we get 8 bits. Those 8 bits need to be offset by some amount. Because if we look at A high, we know it's OX 70, so 0, 1, 1, 1. So 0, 1, let's write it here. Sorry. So you have 0, 1, 1, 1, and we're multiplying that with B low, which was 0, 0, 1, 1. So, wow. So this is a high order part. So if we look at OX70, this is not really 7, the value of 7. It's 7 shifted over by 4. That's what it really is. Do you guys understand that part? So we had A is equal to minus 112, and then we wanted to get the magnitude of that. which is, or like bitwise. So we know minus 112, magnitude is 112. And so we want to find what 112 was. I just had these values already there, like ready for us. And then you get hexadecimal 0x70. Yeah, exactly. I did a 2's complement. Yeah, yeah. Yeah, at the end. So you can have like a register that just acts like a flag or something. Yes? Okay, yeah. So when you're doing A high times B low, you're not really doing 7 times 3. You're really doing 7 shifted over by 4 times 3. So that product is essentially going to be a 12-bit product because what it is 0x70 is just, you're just taking the higher order part, which is 0, 1, 1, 1, and then you're appending essentially invisible zeros like that. And then you're multiplying this by 0, 0, 1, 1. That's the actual multiplication that's going on when you do that. So that's why we shifted it over by 4 bits down here. So it's the same thing with A low times B high. We have to shift that over by 4 bits. But when you do A high times B high, you're doing a value that's shifted by 4 bits and another value that's been shifted by 4 bits. So you need to shift the whole thing by 8 bits. So that's why AB high high is shifted over to the left by 8 bits. Does that answer your question? I'm just doing a smaller example because doing 32 bits would be like way more messier. So I just did an 8-bit times an 8-bit, just splitting it up into 4 4-bit multiplications.
How is 16 split to 8?
Exactly. So for you guys, you have 16-bit number times 16-bit number, but those are split up into 2 bytes in memory each. So this is emulating the same thing, just doing it with 4 bits. So if we move on, I'm going to show you probably the way that the other TAs might have showed you guys if you didn't come see me in office hours. What they do is they don't do this breakdown. They just do direct 2's complement multiplication where you have to do sign extension. So just a quick 4-bit by 4-bit multiplication. We have -2 times 5. So -2 represented in 2's complement is 1, 1, 1, 0. And 5 is 0, 1, 0, 1. So we're just going to, let me empty this out so I can show you guys. So it's just, you're going to do the same multiplication, but now you have to worry about sign extension when you have a 1. So when we do 1, when we see a 1 in the least significant bit here, we're going to write out 0, 1, 1, 1, but then we have to do an extra step. So 0, 1, 1, 1, but now I have to sign extend to fill out a whole byte. So 1, 1, 1, 1. That's the sign extension step that he was talking about earlier. So when you move on to this byte, since it's a 0, you're just going to write all zeros, and you don't have to do sign extension on 0 because that really wouldn't make sense. So you're going to shift over 1 like you usually do, and then just write out all zeros and fill out the byte. Yeah. Yeah, so this is an alternate method. So since we had a 1 here, we're going to write 1 ANDed with all these. So we got 0, 1 AND with that. 1 AND with 1, we got that. 1 AND with 1, we got that. This one and that one, we got 1. But now you need to do a sign extension. So to sign extend it to fill out a whole byte, because our 4 bits times 4 bits is going to give us 8 bits, we need to sign extend. So that's what we did here, is did a sign extension. Yeah?
Or how does that affect it when you need to reset?
For this part? How does it, so if you're splitting it up this way, you have to add certain parts of your 4 8-bit results. So in your case, if you do it this way, for problem 17, you're going to have 4 16-bit results, and you need to find a way to make that one 32-bit number. that's the correct value. But since you split it up into 4 pieces, you have to add certain parts to it to get that correct result. Sorry? Oh, no, this is an alternate method. Yeah, this is you can do this way or you can do something like this. So I was just trying to show both ways, and then Professor Eldon's going to post stuff from his book that shows the same thing. Yeah? Yeah, you would have to break them up. Yeah. The least significant bit, this one? Yeah, that would not hold a sign. That's very true. So for this example, doing it this way, I didn't really work it out, splitting it up, but it's going to be the same thing where you're just going to have to look at the sign. But when you do it with this way, we don't really care what's on the sign bit because we're just doing multiplication the regular way, and we're doing sign extension. So let's say if it was a 0 here, I mean, that's going to make this 6, and let's make this 1. I think that'd be, I don't know what that is. 1, 0, 0, 1, 0. That's going to be 3. Let's say if we did that. So when you do 1, if we do it this way, so you're going to get 0, 1, 1, 0. But I believe you still have to sign extend. You would sign extend this with the zeros.
So would you,
I'm not quite certain on that,
so
though.
in our program, we would have to check either one of them is negative?
Yeah, if you're doing it this way. If you're doing it the 4 8-bit times 8-bit, or 4 16-bit times 16-bit. With this way,
You have to know where
yeah, you would have to know if one of them is negative to do. Yeah, exactly. Then you would just leave it. So I have a link that I can post on Piazza for you guys where I found something like this where they're doing the same thing where they do sign extension. So I'll post these links in this Excel file for you guys so you can look at it. Yeah, so I'm going to post that. So there's no real examples of that online, but I'll post this Excel file that I have, and you guys can go through it and just change the numbers and hopefully get a right answer from that. So they do the same sign extension here, and they have examples of what if you don't do sign extension, you're going to get a wrong answer. So going back to this -2 times 5 example, so we sign extended it, and then you're going to move on to the next digit. Since this is 0, we're going to write out all zeros. So if we look at the next digit, we have a 1. So we're going to do our shift, and then you're going to write out 0, 1, 1, 1, and then sign extend for those rest of the part. And then the last one is 0, so x, 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 0, 0, 0, 0, 0. And then when you add those up, we should get -10. So 0, 1, 1, 0, and then that has a carry of 1, so that's going to be a 1 here, then another carry of 1, another carry of 1, another carry of 1, and a 1 carry out. So if we look at this, F6, that should be -10. There you go. Yeah, so -10. Yeah, so I can go through this one again. So we had -2 times 5. And then what we're doing is we're doing sign extension when we do normal binary multiplication. And then using this method, you can get a correct result without splitting it up. Without doing a 2's complement. We didn't do a 2's complement at all in this part. So we're doing -2 times 5. We look at the first, or the least significant bit of our multiplicand. So we have a 1 here. So we're going to do 1 and with 0, 1 and with that, and that. So we got 0, 1, 1, 1. So from here on out, we have to sign extend because I believe this one was a 1. But I'm not certain on that. I just know we have to sign extend with this. So if you look at the next bit, it's a 0. We're just going to write out all zeros. And we also have to take care of that shift. That's what the X is there for. And then the next one, it was a 1, so you're going to do the same thing. So we get 0, 1, 1, 1, and then we sign extended 2 1s. And then since the last one is 0, we just write out all zeros, and then you add them all up, and then you get the correct value in 2's complement already. You don't have to take a 2's complement of a value here doing this method. Yeah, you don't care about the carryout. Exactly. Yeah. So the carryout is, you don't care. I mean, it might get written to your overflow register, but you don't care about it after that.
Do we manually put that on the register?
No, so you're gonna have a carry in and carry out of your ALU, and that carry out is gonna go feed into like a 1-bit register and just gonna stay there, and then you can have it clear on every clock cycle at the end of it. Yeah, so that's up to you of how you want your overflow register to act. It can stay there, or you can have an instruction to clear it. That's totally up to you. So, yeah, that's this example. And then I was going to just show you guys some assembly code, just random ISA that I'm just coming up with, like not even a full ISA, just show you some instructions, maybe some tips and tricks to help with 18 and 19, because you're going to be stepping through an array. Same in this. Is that too small? Yeah. Yeah. So, just a quick, silly example. Let's say you have an integer array that has 40 elements, and each element has the value of 1 in it, and we just want to get the sum of it. So C or C++ code, this is what you would do, and you should get 40 for sum. So when we're doing this in assembly, we have an array. So the address of the array is equal to the address of the first element of the array. And let's just assume that it begins at memory location 30. So I think for this problem 18, it begins at 32, and it's 64 bytes long. So that would be at memory location 32. But for this example that I'm just coming up with is just to show you some assembly code and show you the basic way, and then maybe show you what you can possibly do for a complex instruction that can save you some instructions that would do 2 things or something. So I'm assuming that I have R0 to R15, and I'm using R0 as my accumulator register. And then these are just some, I didn't really get to fill out the rest of this, but just some sample instructions that I have. So I have my load immediate, where I have an instruction that loads an immediate into my accumulator register. I have a load byte instruction that goes to the memory address pointed by register that I supply as an operand, and it loads it into our accumulator. I have a move instruction that just copies the value in our accumulator to another register that I supply in addition. And branch, I have a branch instruction because you're going to need some form of control flow in your assembly code. So you have to have some form of branching and then use of conditionals, because how are you going to check your loop conditions to break out or not? You have to have some instructions that take care of that for you. So in Professor Eldon's lecture, he had like a be even branch. So what a be even branch was, it would just check the least significant bit of some register operand and see if it's 1 or 0. And if it's 1, or if it's 0, it would branch, because that means that that value was even. And if it's 1, then you don't branch. So you have to have some way to do conditionals. So just to emulate this code using some of these instructions, I might have to add some because I didn't get to finish it, but I'll step through it with you guys. And after this, I'll show you how to increment. So over here, you're not going to add 4 to the base memory location each time, because that's going to waste some instructions. You can possibly have an instruction that takes a base address and then just increments that and loads it back into a register. Yeah? I'm just calling it R0. Yeah, so it's going to be, you're going to index everything like an array. So you're going to have an index 0. So I just called it R0. This is more of a load store ISA than a stack. So I'm just doing it more like MIPS would. Yeah. So the first thing you want to do when you have a loop in assembly is you want to check your conditional. So I'm not loading the immediate value of 40 into a register because I don't want to waste a register. Let's say I only have 8 registers instead of this many. Why waste a register on a constant? So what you can do is you can just do load immediate 40. So what that's going to do is set, let's write it easier this way. R0 is equal to 40. And then you want to check to see if let's say we have R1 is our loop counter. And that's set to 0. So you can assume at the beginning of your program that registers are 0, like are all zeroed out, or you can even preload values. So you can save some instructions where you can, at the start of your program, you can assume that your registers are filled with whatever you want, and your data memory, besides the saved portions that we have for the byte array and the other values. So let's say I wanted to have 40, so I don't want to do this step, and I want to load 40 into R0. You can assume at the start of your program that 40 is already there, because you're going to be making a file for your data memory that is going to be read into your actual data memory module, and you can make a file, like a text file, for your registers where you're going to read it. You're going to read those registers and just load them in at the start of your program in the Verilog side, like on a test bench. So you can assume that. So you can save a few instructions at the beginning for that. So I'm assuming that R1 has my loop counter, and I'm loading 40 into R0. So I want to check to see if my loop counter is less than 40. So I'm going to do set less than. So I have this right here, if RS is less than RT. So RS for me would be my loop counter R1. And I want to see if it's less than 40, because 40 is stored in R0 now. So if it is less than, then it's going to set my overflow bit. So that's what I said here, is that R overflow is equal to 1 if RS is less than RT. Otherwise, it's equal to 0. So the condition that I'm looking for to branch is if R overflow is equal to 0, meaning that it's not less than. So I can make use of ENEZ, branch not equal to 0. It's going to be the same as this. So I can do BNEZ, and then somewhere around here, I'm going to have end loop. So this just checks to see if my loop is okay, like at the beginning, because we're going to be branching back somewhere over here. Branch loop. So you don't even, over here, I didn't even specify any register operands for these branch instructions. So that's totally up to you how you want to handle that. So let's say you don't want to look at R overflow, or if you're set less than, instead of saving it to your overflow register, it saves it to a register. Then you can specify that register to your branch instruction. All that is totally up to you. So now what I want to do is load my first byte from memory. So I'm going to make another assumption that R2 is equal to 30, which was base memory location of array. Yeah.
What happens to your overflow register? Is using like after you do this arithmetic and algorithm, you do need to use the overflow bit, but you happen to have to use set less than it.
Yeah, so it's going to kick the existing value that's in there. It's going to kick it out, and it's going to go going to go poof, and then that value that is writing, or that instruction that does write to an overflow, it's going to update it. So not all instructions need to write to the overflow register, just ones that you decide.
So we have to include that.
Yeah, in the write-up. Exactly. Yep. So, yeah, another question? 32? So what this is saying is that if R1 is less than R0, then the overflow register will be equal to 1. We're going to set it to 1. If it's not, then we're not going to set it to anything. It's just going to be set to 0. So that's what that's doing. Because we need to have a way of checking if our counter is less than 40. So it's basically doing the same thing as this, right there. That's all that's doing.
Is the overflow register one of the?
No, that does not count because that's just a 1-bit register. So that doesn't count against your 16 at all. So the other assumption I made was that R2 is equal to 30, and that's our base memory location. So I want to do a load byte. So I can do load byte. Yeah.
I guess my earlier question was, because you're definitely going to use the overflow bits for your arithmetic, right? For like multiplication or something like that.
Yeah, just for your add. That's the only one where I see that you're using overflow.
What happens if you do an add and then you set less than?
So if you do an add, your overflow gets written, and then when you do a set less than, your overflow is going to get overwritten.
Because you actually want that validation.
Yeah, so you're going to have some logic in between that checks or does something with whatever it was intended to do with that overflow. So having an add instruction and the set less than immediate after that, where you have to do something with that overflow, doesn't really make sense, because you're going to have to do something. If that add is important to something, then you want to have that logic in there in between that add and set less than. Or you can save it to a register using a mask. You can AND or have a special instruction that extracts it and saves it into a register. You can have those things. Yes, exactly. I mean, you don't have to do it this way. I mean, this is just one of many ways to go about this. So instead of using overflow register, I could be using just an actual register. Let's say you have 16 registers and you can use all of them. You don't have a register problem. So the point I'm trying to make here with some of this stuff is don't waste registers in your assembly code on stupid things, especially with immediates for loop counters. Because you can just have this one instruction at the beginning that loads up 40 because you as a programmer know the limit of what your loop will be. So for the problem 18, you know that you're looking at 64 bytes. So you can just load immediate 64 at the beginning of the loop every time. You don't have to save 64 in one register and have it stay there and not get overridden. That's what I mean by that. Yeah. Yeah, so I just saved it. So for this load immediate, I didn't want to specify a register. I'm just having it save to that one register. Yeah. So when you're going to work out the details of that in the future labs, where your control signal is you're going to decode load immediate, and then your control is going to set, you might have a mux for your write register, and it's going to select which register you want to write to by specifying it. And you might just have R0 there as a constant. So the load immediate instruction will select your write register as R0. So going down over here, I'm just going to we want to load byte and get the actual value, what's in memory. So this is a unary instruction the way I have it set up. It doesn't have to be that way because you can give RT as, I don't have to give R0 here. It can be any register, but the value in memory is being stored back into R0. It just happens to be for this example that that's what it was. One second. I actually have a mistake. It's R2, actually. Yeah. Because what we want to do, what that means is R0 is equal to mem R2, which is the same thing as mem 30. That's what I mean by that. So that's going to get the value. And then let's just say I'm using R3 to hold sum, just be sum. Then I had an add here, so I can just do add R3 and R2. And that's going to incrementally or continuously add the value of my byte to R3. So this is just saying sum plus equals R2. So now that I've done this, I want to increment R2 because, well, I've lost the value of 30 by doing load byte here. So maybe I didn't want to use R2 here. I can do something. Well, one sec. So R0. Yeah, sorry. This is R0. Yeah. So 40 was just, I have an array of 40 elements. So I want to iterate through each one and add the value that's in each element. So I need to check. So this is like I equal to 0, or this is just doing I less than 40. These two lines, they're just checking to see if my loop limit is less than the number of elements in my array. So it's the same thing as doing this in a for loop. It's the same thing. Instead of storing 40 into a register, I just want to not use a register like every time and have that register be persistent through my whole program. I can just load that immediate value at the beginning. That's all that's doing. So this is just, because this load byte, it set R0 equal to memory location R2. So R2 still has 30 in it. So what I want to do to R2 is I want to increment that. So I can have an increment instruction. And what that will do is RS, that's the register that we're supplying. Plus equal to 1. It's just adding 1 to the value of that register. So I can do increment R2. And then that's where my branch instruction would come run. And then that does that simple program of summing it all up. And that sum is stored in R3. So if you look at this, we had 2 instructions to load the value of what was in memory and to also increment that base address up by 1. Now, I also forgot one step. We want to do increment R1 because we want to increment our loop counter. That's I++. So what you can do is you can technically combine these 2 instructions, come up with an instruction that will go and load something from memory at that address and store it into R0, and then at the same time increment the value of that base address. That's totally legal. You're going to have to draw it out and figure out your data path later on, but you can, instead of doing 2 instructions here, we're going to add that as 1 instruction. Yeah?
Use R0 to store that counter, but within the loop, you use R0 again just to store that immediate value.
So over here, R1 is my loop counter. So R1 is initially 0.
But then your R0 won't be 40 in the next loop, right? Then next time you check your R0, so it can be modified.
Yeah, so when you come back here, we don't care what R0 is. Yeah, we don't care about the value of R0 after this line. We don't care what happens to it. Exactly, yeah. Yep. Because you're going to be running that instruction in code anyways. by doing it this way. This was the strategy I implemented because I only had 8 registers. So I couldn't contain everything in my program just using 8 registers. So I did tricks like that to like, hey, I don't need to keep track of my loop limit when I can just check it at the beginning and with one extra instruction. Yeah. Yeah, I guess.
So this is the accumulator approach?
This was like a load store. This was like a hybrid where I'm using accumulator where some instructions are just going to one register and then
memory address, why do you just increment by 1 since like you would need wouldn't you need to increment by 4 instead?
So 4 is for a 32-bit system where this is an 8-bit system. So we're just incrementing by a byte. Yeah.
So
Yeah.
basically, your this strategy is to reuse one register, like whatever operation is just the one you use, right?
Yeah, that's if you're strained on registers. You know, if you have 16 registers, you can definitely do the programs. You won't have to worry about registers. But if you had 8 like me, then it's going to get a little tough, you know?
So
Yeah.
for us, how many do you have? 16?
Yeah, no, it's up to you. You can have up to 16 or less. I mean,
The less means that we're going to use less bits, so this is
yeah, so
So it means that we can like do the same thing like that, but like let's say if there's 2 operands, we just use the same 2 registers to store the operands, something like that.
yeah, you can do it that way. You can come see me in office hours and I can show you some tricks where people had 16 registers, but they only used 3 bits to address.
16 registers, 3 bits.
Yeah, so what they did with that 3 bits was that those 3 bits were addressing just the first half. And then the other 3 bits for the second operand were addressing the second half. You know, they did tricks like that, you know?
That's pretty cool.
Yeah, so it's totally up to you to get creative and
Okay.
find tricks and hacks for that. Yeah.
I just want to ask, you're posting this on TED or
Yeah, no, I'll post all this on TED.
Oh, okay. This
Or
is
on Piazza, yeah.
on Piazza relevant.
Yeah.
This is relevant to 18 and 19?
Yeah, it is very relevant for 1819, yeah.
Like, through and away. Okay.
Yeah,
Thank you.
no problem.